So in the last video, we introduced the fundamental theorem of calculus, and what we said is, if you can find some other function that when you take its derivative, you got the thing you were going to integrate, you could actually use that to evaluate definite integrals. So we want to be able to find that something that we need more efficiently. And that something that we need is actually what we call an antiderivative. So an antiderivative is the following. If the derivative of some function f, uppercase f, is lowercase f, we say uppercase f is an antiderivative of the lowercase f. So the idea is if you had x squared, that would be our uppercase function. X squared is an antiderivative of 2x. Why? Because if you took the derivative of x squared, you would get 2x. Now notice I said is an antiderivative. The reason is, what about the following? X squared plus 5, x squared minus 3, x squared plus 11,245. If you took the derivative of each one of these, you would get 2x, because the derivative of x squared is 2x and the derivative of a constant 0. This would also be 2x. This would also be 2x. They would all be 2x. In fact, all of those expressions are antiderivatives. Any x squared plus c would be an antiderivative of 2x. So x squared plus or minus any number, if you took the derivative of it, you would get 2x. So those would all be antiderivatives. So we say this is a family of antiderivatives. Any function has a family of antiderivatives because we can always add a plus c. So just a notation, we've previously done what we call definite integrals. We've had some a and some b number here. We're actually going to take those numbers away. And if you just have this general integral sign, dx, no limits to try and sort out or figure out what area we're trying to cover, this is what we call the indefinite integral. And the answer to it is to find something that when you take the derivative of it, you would get x squared. And the answer here is actually 1/3 x cubed plus c. So if we're finding these indefinite integrals, you're always going to add a c. And you're probably thinking, well, how do I know to come up with 1/3 x cubed? You can always check. If I was to take the derivative of that, right, we would drop down 3. 3 times the third is just 1, and reduce it by 1. You'd get x squared, and the derivative of c is 0. So that would give us the original thing. So we always add this plus c to it. Well, now we're going to try and answer the question, where did the 1/3 come from? How did I know to do that? We have a list of common antiderivatives, and this is something you should know. If you have not been printing out your notes, I would definitely say this is a good page to print out because you're going to want this list of rules. And so if we just briefly talk through them, if you want to find the general antiderivative of just a number, it's actually that number times x plus c. Because if you took the derivative, and really if you thought of that of a line, kx plus c, if you took the derivative of that, the answer would just be k. If you want to find the antiderivative of x to some n, you do 1 over n plus 1, x to the n plus 1, plus c. This is actually how I knew to come up with that 1/3, and we'll see how to use that in a second. And note, this is only for n not equal to -1. The reason is actually the one below it. If n equaled -1, you would have 1 over x. Well, remember the derivative of natural log was 1 over x. So if you want to do the antiderivative of 1 over x, it's going to be natural log, and we add this absolute value to it. Natural log absolute value of x plus c. The antiderivative of cosine x dx is sine x, and that's because the derivative of sine is cosine. The antiderivative of sine is negative cosine, and we actually did that in our previous example because the derivative of cosine is negative sine, we need to add an additional negative. And the antiderivative of e to the x dx, or if we want to evaluate e to the x dx, is just e to the x plus c, because the derivative of e to the x is e to the x. Alright, so a couple examples. If we wanted to find the general antiderivative x to the fifth, we're going to use x to the n dx, which we know is now 1 over n plus 1, x to the n plus 1, plus c. So in our example, n is just 5. So x to the fifth dx in this case would be 1 over 5 plus 1, x to the 5 plus 1, plus c. We get 1/6 x to the 6 plus c. If we want to find the antiderivative of just the constant 4, we're going to use this one here. So if we do this where 4 is in place of k, we would get 4x plus c. And if we took the derivative of 4x plus c, you would get 4. A couple other unique examples. The square root of x. What are we going to do with that? Well, we're actually going to use this one again. This x to the n dx equals 1 over n plus 1 x to the n plus 1 plus c. And we're going to rewrite this antiderivative as x. And if you remember, we can rewrite that square root as 1/2. And so now I can see my n is 1/2. So using that, we would have 1 over 1/2 plus 1, x to the 1/2 plus 1, plus c. Simplifying that, we give us 1 over 3 over 2, x to the 3 over 2, plus c, which 1 over 3 over 2, if you use some properties of division of fractions, you would see that really simplifies to 2 over 3, x to the 3 over 2, plus c. If you had the antiderivative of 1 over x to the fourth, you need to resist that urge to want to use that natural log one. That only applies to 1 over x. If it's 1 over x to the fourth, we need to rewrite that as x to the -4 dx. Now we can use that same rule, and I would say that equals 1 over -4 plus 1, x to the -4 plus 1, plus c. That's 1 over -3, x to the -3 plus c. And we can simplify that. That's really -1 over 3x cubed plus c. A couple important properties. If you have c times some function, you can take c out and then do the antiderivative of that function. If you have one function plus or minus another function, you can separate that and find the antiderivative of each one individually. So for this example, I had the antiderivative of 5 over x. I'm going to first rewrite that by taking out the 5. 5 is just a constant. So I have 5 times the antiderivative of 1 over x dx. Now, as we previously discussed, the antiderivative of 1 over x is natural log absolute value of x. So this would be 5 times the natural log absolute value of x plus c. Okay, we're going to use both those properties for this one. I'm going to do a lot of rewriting here. I'm going to rewrite that as 3 times the antiderivative of sine x plus, I'm going to pull out that 1/5, the antiderivative cosine x, and we're going to find each one of those now. So 3, and the antiderivative of sine of x is negative cosine x plus 1/5. The antiderivative of cosine x is sine x, and we always add a plus c. And then just to simplify, 3 times negative cosine x, I'm going to rewrite that as negative 3 cosine x plus 1/5 sine x plus c. Okay, here we've got a nice long one. We've got 3 different functions essentially going on there. I can rewrite this whole thing. I'm going to pull that 5 out. 5 times the antiderivative of e of x dx plus 2 times the antiderivative of x cubed dx minus 5 times the antiderivative sine x dx. And we're going to go through and find each one. Well, the antiderivative of e to the x is e to the x, so that one's easy. 5 e to the x plus 2 times x to the third. We use that power rule, x to the n rule. 1 over 3 plus 1, x to the 3 plus 1. Minus 5 times the antiderivative of sine is actually negative cosine. We always add a plus c. So just going through and simplifying this, you have 5 e to the x plus 2 times a fourth is really just 1/2 x to the fourth. A negative times a negative, positive 5 cosine x plus c. Alright, last example. Now that we know how to quickly find antiderivatives, we can actually quickly do a definite integral because we can find the thing we're trying to plug pi over 4 and 0 into. So let's real quick find the antiderivative of 2 sine x dx would actually be negative 2 cosine x plus c. Well, for doing a definite integral, we just need something in general to plug into that if we took the derivative of it, you would get 2 sine x. And so the answers, we're just really going to use negative 2 cosine x. So to evaluate this definite integral from 0 to pi over 4, 2 sine x dx, we're going to plug pi over 4 into negative 2 cosine pi over 4 minus, plugging in 0, negative 2 cosine of 0. That gives us negative 2 times cosine of pi over 4, which we could evaluate with a unit circle and see that that is square root of 2 over 2, minus negative 2, and we know cosine of 0 is actually 1. So that gives me negative 2 over 2 is really negative square root of 2 plus 2. And we can leave that answer like that because we don't have a way to necessarily add those two. So that would actually be about as simplified as we can make that answer.